Hello? Oh, cool. Hello, everybody. This is Papers We Love number, I think, is 8. Good. So I'm very happy to see everybody here. I have some new recurring faces and faces that are new. The admin trivia for this month is that we have Armin today talking about swim. Then we have Cal Kingsbury coming next month to talk about something that he has yet not told me. Then from the New York chapter, we have Leif Walsh, and then he's going to talk about data structures and mostly like trees, so that is going to be really nice. And in December, we have Peter Baylis also with a topic that he's going to pick. If you're interested in speaking next year, look me up or let me know, because I'm covered till February, but I'm looking for speakers for next year. So if you have an itch or if you have something that you really like and you want to share with the group, let me know. So I'm going to turn it to you so you can.
All right.
Yes.
Hi, everyone. Welcome to Fastly. We are a content delivery network. We specialize in caching dynamic content. We're very excited to have you all here. We're excited to have Inez joining us very soon. Yes. And if you have any community events, meetups, events outside of this that you're interested in having us host, please let me know or email me or Elaine, KCACIE @fastly.com, or you can talk to Inez. And we love hosting events like this, and we're interested in doing more of it. Welcome.
Cool. Thank you guys very much. Thanks, Inez, and thanks, Fastly, for you guys sponsoring this and letting us make use of your space. So today we're going to talk about swim. We're going to come back to its title in a little bit to unpack it, but just to provide some context, for those of you who don't know me, my name is Armand. You'll find me around the internet as just Armand, and I work at HashiCorp. For those of you who are maybe familiar with HashiCorp, maybe not, we are a DevOps tools company. So we make tools for developers and operations people. You may recognize some of our tools. We make Vagrant, Surf, Consul, Packer, and Terraform. And we're going to come back to this in a little bit, but Swim is actually a pretty core technology to both Surf and Consul. And we'll come back to kind of how they make use of this. So to kind of, before we can kind of really dive into the paper, one of the problems with a lot of these white papers is they kind of assume a certain context, which is, in this case, Swim is a membership protocol, but what is a membership protocol? What problem do membership protocols solve? And so the problem space they focus on is, suppose you have a dynamic group of members. So you have a set of servers, they're running some process, and they're coming up and going down. And and they're communicating over a network, presumably, and because it's a real network, you have packet loss and network partitions. And the question we'd really like to answer is, who are my live peers in this kind of a setting? And so the goal of the membership protocol is, the membership part of it is, who are the peers, and the failure detection part, which is kind of implicit, is, are they alive? And so the use cases are pretty varied. So given that you have an algorithm that's going to give you a list of live peers, you can do things like build a peer-to-peer network. So maybe you want to do file sharing, and you need to know who are the other peers that I'm communicating to exchange files. You could be building a network overlay, for example, a content distribution network like Fastly. Or you could use it as a primitive, a discovery layer within a larger distributed system. For example, I know Basho makes use of gossip protocols in Riak to know who all are the content serving peers. And this is the case for both Surf and Consul as well. So Swim, basically, this is a mouthful, but it's the scalable, weakly consistent, infection-style process group membership protocol. And out of the respect for the authors' names, I'm not going to attempt to butcher them. Those are the authors. So let's unpack the name a little bit. There's 4 kind of key components here. The first one is scalable. So in the context of a gossip protocol, what this expectation that should be set here is that it's not an algorithm we expect to run on a handful of nodes or a dozen nodes. It really should be something that we're evaluating at the 100-node, 1,000-node, 10,000-node scale, right? There's almost any membership algorithm you can get it to work if you only have 5 nodes, right? So it's not a very interesting problem space. Weakly consistent, we should expect that all nodes are going to have differing views of the state at any given time, but eventually we expect to converge. And so this, as we go into the paper, should set kind of expectations of certain design decisions. Infection style is a synonym for gossip or epidemic, and it basically means we're going to exchange state updates with a subset of our peers, and through kind of a random process, we expect this to permeate out through to the entire cluster. Lastly, membership protocol goes back to our last slide. We expect this thing to solve the question, who are my live peers? Okay, so jumping into kind of the first question is scalable. So the paper opens up right away, right in the abstract with this quote, "The SWIM effort is motivated by the unscalability of traditional heart beating protocols." So to kind of look at the paper, we have to put it into the context of when it was written, and at that time, heart beating was the considered state of the art. So to kind of compare it and show how progress has been made by SWIM, we really have to understand what state of the art was at that time. So heart beating fundamentally is a really simple idea. For every process, we pick some time interval of gossip t. So let's say 1 second. So every second, we notify our peers that we're alive. So we say, hey, I'm node A, I'm still alive. A second from now, I continue to say I'm alive. Every peer then waits and says, if I don't hear from a given peer that I knew about previously, after some limited number of rounds, I'm going to mark it as dead. So we can set limit to be 10, and every second, node A says I'm alive, and then at some point, node A dies, or the network fails, or something happens, and it stops sending this message. And 10 rounds in, we say, node A appears to be dead. Drop him from your list of live peers. So in this way, heart beating kind of very elegantly gives us both membership and failure detection. All we have to do to join the cluster is announce that I'm A and I'm alive. Great, I'm now a member, people think I'm alive. And the failure detection is when I stop announcing, eventually people just believe I'm dead. So it's a very simple algorithm, very understandable, and it gives us a very basic membership protocol. So the question becomes, how do you implement heart beating? Well, one approach is basically a broadcast approach. This can be done either with IP broadcast, IP multicast is a bit of an optimization, but basically you're going to say we're going to use a network level technology. I'm just going to push this problem onto the network. I want to send a UDP packet, make sure it gets delivered to everyone on my subnet, and say I'm alive. Well, one problem with this is that in most real-world environments, broadcast and multicast aren't enabled in the first place. For example, EC2 is a multi-tenant environment. You can't trust that your clients aren't generating, thousands of broadcast messages a second, so you just disable it. That's the way you get around it with policy. And in most real-world networking environments, it's disabled. So that's not a great approach. The other approach is to use gossip, and basically, I'm going to send my alive message to one peer, he's going to forward it on to another peer, and so on and so forth, and everybody will know I'm alive. So there is some past work in making heart beating work and getting around the limitations of both broadcast and multicast. But again, it's not perfect. And the reason it's not perfect is basically you have n nodes, and every interval, your n nodes are sending a message to every other node, right? And so we can see that basically the cost of this is n squared, right? Which might be okay if we have 10 nodes. That means every second we're maybe sending 100 messages. But quickly, if you're at 1,000 nodes, well, now we're sending 1,000,000 messages a second. And if we're at 1,000 nodes, we can't really use IP broadcast or multicast. We have to use gossip. So there's a log n multiplier, and now we're sending 10 million messages every second. All of a sudden, this looks like an incredibly impractical approach. So the paper sets out a kind of a rubric for evaluating different membership protocols. And this comes from a different paper, actually, earlier in the literature. And it basically breaks out the evaluation into 4 distinct kind of axes. One axis is strong completeness, which is, does every live member eventually detect every failed member as such? So, given we have a list of peers, I want to know at some point that, a given peer has failed. The next is basically speed of failure detection. So how fast do we go from a failure to at least one peer detecting that failure? The next is accuracy. So, what is the rate at which we declare a node to be failed when it in fact isn't? And so you might ask, this is kind of a weird axis. Technically we would want it to this should never happen. Unfortunately, there's an impossibility proof that says, given that we have an async network, and given that strong completeness is a hard requirement, it's actually impossible to have a perfectly accurate failure detector. We won't get into that, but basically, it's enough to know that accuracy is a concern we have to worry about. And then the final one is network message load, which is just, what is the load in the network? So if we want to look at heart beating and evaluate it against this rubric, then we look at completeness and we say, yeah, every node is receiving these heartbeats. And so every node can independently decide after a limit period of time that a given node has failed. So all the healthy nodes will detect that all the non-healthy nodes have failed. The speed of detection is tunable. So there's our gossip interval, which let's say is 1 second, and the limited number of failure rounds, which is 10 seconds. Again, we can tune this, and this is kind of where we get this trade-off between speed and accuracy that we're going to see again, which is, let's say my limit is only 1 round. It could be that one packet was dropped, and now I'm going to mark it as failed. And in that case, my accuracy is probably fairly low given packet loss. But if my limit, approaches infinity, then my accuracy also, asymptotically approaches 1. So given, that you can model some sane network condition, you can set your limit such that your accuracy is, specifiably high. But the trade-off is between speed and accuracy. Now, the big problem, as we talked about, is the load. In the case of heart beating, we have an n squared in here. And the reason it's bold is because that's simply not going to work for most practical situations. You just can't get away with an n squared, especially, at 1,000. 10 million a second is pretty insane. If you want to go to 10,000, all of a sudden you're in the hundreds of millions or billions, and it's just like your network will implode. So we can't do that. So the insight that the SWIM authors had is really, we have 2 separate problems with a membership protocol. One is basically the failure detection. So given a set of peers, how do you know which of them are alive? And then the other one is, what is the set of peers, right? So that sentence can actually be turned into 2 parts, which is that live part and the peers part. And if we kind of make this separation and separate our concerns, then there's a question of, well, can we do it better on the failure detection component? And the SWIM paper basically presents a completely novel approach to this, where the answer is yes. So they provide what I'm going to refer to it as a ping-based failure detector, but it's the SWIM failure detector. And it's a very, very simple algorithm. All we do is every interval of gossip, so every second, we select one of our peers that we think is alive, and we send them a ping message. And if they're alive, they respond to us with an ACK message. Well, already we can see, I'm sorry, one key of this is that we pick a random peer at every second. So, we just happen to pick this peer, 2. And so if you start to think about this, we're like, okay, well, we know that because we're randomly picking, we expect that we're going to, at some point, ping everybody. So if a given node fails, eventually we're going to get around to pinging them, and we're going to be able to figure out they're dead. So great, we seem to have completeness. And then we have speed of detection, which is, it looks like it's going to be pretty fast. If we ping them and they don't respond within a round trip time, we declare them as dead, looking pretty good. And then there's accuracy. There's an accuracy issue here, which is, suppose our ping message gets dropped. Well, the peer has no chance to send an ACK back. Suppose the ACK is dropped. We have no way of knowing whether they actually received the ping, and we just failed to receive the ACK. So how do we kind of improve the accuracy? Well, the authors had this idea of an indirect ping. So suppose we send the original ping, the node fails to send the ACK back, or maybe it sends the ACK back and it gets dropped. What we now do is we pick k number, and this k is configurable, we'll get back to it, of other random peers, and we'll tell them, hey, can you indirectly ping this guy? So we pick these other 2 peers randomly. We tell them, hey, do an indirect ping. If they happen to receive an ACK back, then they go ahead and forward it to us. And basically, the whole reason this technique exists is we're guarding against packet loss. So if our original ping is lost or the original ACK is lost, then we wait some round trip interval, and now we're saying, okay, let's give the peer a benefit of the doubt. They're probably alive. The network is always at fault. Let's go ahead and ping through some other peers and give it another chance to basically respond to us. And this way, by going through other random peers, we're going to pick different paths through the network. It might be a less congested path, or maybe we just get lucky and the buffers decide not to drop us this time around. Either way, we now have multiple opportunities for the node to respond. So now if we want to evaluate this technique using the same rubric, again, the completeness as well, we expect every node is going to be pinged at some point, just given that we're randomly picking nodes. There is a caveat here. We'll get back to that, but you might be thinking, well, there's a pathological case here. The speed of detection, using a simple ping ACK, is just a single interval. We're going to send the ping. If they respond within 1 round trip time, they're alive, and then we're going to send the indirect pings. They have until the end of the interval for some ACK to get to us. If we receive no ACKs by the end of it, then we can mark them as dead. So our speed is only a single interval, which could reasonably be 1 second. Then our false positive rate, this one is, I've simplified it a lot if you went through the paper. It was a much larger equation. But basically, given that we have a reasonably healthy percentage of our cluster such that, like 90% of it hasn't failed, roughly our false positive rate is, what is the chance that original ping ACK is going to be lost? And then what is the chance that our indirect ones are going to be lost? That's why we have that k exponent. And so because we have a small number raised to a power, basically we can get this number to collapse towards 0 by just increasing that k by very small amounts. So for example, if we select a number like k equals 3, well, all of a sudden 0.01 raised to the third, it becomes like 0.00001, right? So our accuracy jumps up and we can get it very nearly close to 100% if we're worried specifically about the packet loss situation. We'll come back to this because there's other things we might want to guard against. For example, we're only giving a 1-second interval of detection. It's entirely possible that the switch is rebooting and the switch is actually just going to be gone for 3 seconds. So in that case, it's not a random packet loss we're worried about. It's more of a short-term persistent problem. We'll come back to how we resolve that. Now the real key here, though, is the network load. If we think about kind of the process to the failure detector, it sends a ping, we get an ACK back, but it's happening from one node directly to the other node. We're not sending a heartbeat from one node to every other node. And the difference is now we've moved from an n squared to an O of n. Effectively, we have 2 packets, the ping and the ACK, and then there's the optional 4k, which is whatever our k is, and that's not even the expected case. That's only if they fail to respond to our ACK. But anyways, doesn't matter. We're on O of n, basically. So now our 10,000 node cluster only has to send 10,000 packets as opposed to 1 billion packets. All of a sudden, this is a reasonable approach. Okay, so we've split out the failure detector from the membership part. So we still have a problem, which is, well, how do we handle the state updates? We still have to, disseminate who are the set of peers such that, we can actually bother to detect whether or not they're alive. So we can kind of split this problem into, we only really have to send 2 kinds of messages. One, which is a node is alive and has joined our network, and the node appears to be dead message, right? And again, we have the same kind of choices that we had with the heartbeating approach. We can use IP-based broadcast and multicast. But again, this runs into all the same problems. You can really only run it on a few subnets. Most of the time it's disabled. You can't use it in the public cloud. Packet loss is terrible, blah, blah, blah. So then we go back to the gossip-based approach, which is, okay, how can we do a peer-to-peer system which doesn't require any special networking support? And yes, there's a multiplier of log n messages, but we get around this kind of broadcast multicast problem. So the clever idea that the SWIM authors had is, well, we're already picking a random peer, and we're already sending them a ping and an ACK. And this ping and an ACK is very small, right? We got to send 1 byte to the node that says ping, and they're sending 1 byte back that's ACK, and we have all these other bytes sitting in that packet that we could use. Why don't we just make use of it to send state update information? So they introduced this piggybacking approach, which is do your randomized gossip the randomized failure detection exactly the way you're doing it before, but now you can introduce state updates as well to that message. So for example, suppose node B joins our cluster. It just sends a ping to A, looks like any other ping A would receive, but it now says, hey, there's a new node B. And A responds and says, ACK, also meet node C, he's already in the cluster. And the next time A is pinging C, it informs C that, hey, node B has now joined. C might take the opportunity to respond, hey, I've detected that D is dead, you should remove him from your peer set. So in this way, we're able to send maybe 5 to 10 additional state update messages with every ping and ACK that we're sending. And effectively, what we've now built is a gossip layer. So this is the infection style part of the title. Because the ping is sent to a random node, we're able to, in log n time, send these state updates to our entire cluster. There's a bunch of math on the paper that goes through and shows this, and this is kind of out of the study of epidemic spread of bacteria, actually. So oddly relevant with Ebola. And basically, because of this process of picking random peers and sending state updates, the weakly consistent or eventually consistent part of it naturally falls out. The first node to detect that D failed, it knows that state update before anyone else does. It then, on the next interval, gossips it out to the next 1 peer. Now 2 of them are aware that D is dead, but everyone else thinks D is still alive. And slowly over time, everyone will converge onto thinking D is dead. So in this way, some nodes have access to information before other nodes do, and so the state update is only eventually consistent. And because the updates are sent peer-to-peer, it's infection style or gossip style or epidemic style. Yeah, they're all kind of the same. So this is kind of the initial part of the paper. It lays out this groundwork. So we have a ping detector, and by making use of piggybacking, well, we satisfy both the live part as well as the peers part, and so now we have a full-fledged membership protocol. But how do we get to SWIM++? How do we kind of address some of the shortcomings it has? And so there's two additional techniques that get introduced by the paper. One is the suspicion state, and the other is time-bounded completeness. So let's look at the suspicion state. So the first problem is that, as we talked about with accuracy, we're only guarding against very, very short-term random packet loss by doing the indirect ping. So basically, our ping detector is giving us k+1 chances within a single interval to respond. However, we have other types of failures that we'd like to guard against. For example, you're running a Java process, it decides to GC for 90 seconds, it falls off the face of the earth. It doesn't matter if the network has 100% deliverability, it's still not going to respond to those messages. How do we guard against these kinds of situations such that we can reduce our rate of false positives? And so we know we can't sacrifice strong completeness, and we know basically there's some kind of fixed relationship here between our false positive time and our failure detection time. So what we'd like to be able to do is say, you know, it's okay if we don't detect the failure within 1 second. I'd rather detect the failure within 10 seconds, but have a much lower false positive rate. It might be very expensive, for example, to handle a false positive. Maybe a node leaves your database thing, and you're like, oh shit, I better start moving data between other replicas. This is particularly expensive, and you would rather maybe just wait an additional 10 seconds and be sure the node has failed. So the way we fix this is by introducing an additional suspicion state. So before we did the ping, if we didn't get the ACK back, we sent a message saying, hey, this node is dead. So in this case, we do our ping, the node is busy, whatever, it's overwhelmed. Then we do an indirect ping. Those guys also send their pings, but there's no ACK received. So this time around, what we do is, when we talk to our other peer, we don't actually say that C is dead. What we do is we say, we suspect that C may have failed. And B says, okay, great, I acknowledge. And the suspect state is kind of this intermediary between being alive and between being dead. So for all practical purposes, a node that is suspected of being dead is still treated as being alive. We don't report to the application yet that it's dead. So the aliveness is kind of a Boolean. When a client asks what is the list of live peers, you return both live and suspected nodes still. But what this now does is we have an additional opportunity here to basically refute our own death. So someone tries to ping us, we're busy for a while, great, we don't get around to it. So they send the suspect message out, and this gets gossip to the entire cluster. So now everyone transitions to believing that we are in a suspected state, but now we have this opportunity to refute. So we ourselves receive a message that says, hey, I suspect you're dead, and you say, okay, that's kind of weird. I'm going to send back a message saying I'm actually alive. So you refute that gets gossiped back out, and everyone transitions back to thinking you're in the alive state. If you don't respond to this, for example, maybe you're actually dead, maybe there's a network partition, who knows, a timeout is reached. This timeout is configurable by the client. You basically transition to the dead state. Now, it might be that you only gave yourself a 10-second timeout period. Java's GCing for 90 seconds. It eventually comes back and refutes itself back out into the alive state. So it's possible to still recover from being marked as dead. But basically, you now have this configurable timeout value, which lets you select your false positive rate and guard against other kinds of failure cases. So this kind of leads us into another problem, which is that networks are really fun. So one problem we have is that our gossip is randomized. We're picking random nodes to send these state updates to, and as a result of this, we're already sending state updates out of order. But worse than that, the network is also free to reorder our packets and to drop packets entirely. So this can create all sorts of confusion. For example, we can have the two perfectly valid set of packets, and they arrive at two different nodes and in a different ordering. So in this particular ordering, machine number 1 sees, okay, A is alive, great, it joined the cluster. It's entered the suspected state, maybe it failed the pings. A is marked as dead, timeout must have been reached. A is alive. Maybe it rejoined, it refuted, whatever. At the end of this state transition arc, though, node number 1 believes A is alive. Okay? With message Q2, we receive alive, suspect, alive, dead, but this has a very different interpretation. At the end of applying this, we end up in the dead state of our state arc. So now the problem is, given the exact same set of packets transmitted over our network, we have two very different set of interpretations and no way to reconcile them. We have no way to know if one node believes A is alive and another node believes A is dead. We have no way of knowing whether A is actually alive or dead. So we would like a solution to this problem. So what we'd like is order from chaos. And so, one option is we impose a global ordering on all messages sent in the system. Unfortunately, this is a very coordination-heavy activity, and all of a sudden now you need consensus. And so now you're in kind of this super crappy world of needing leader election and serializability and linearizability, and that's not something we want to deal with. Luckily, the authors noticed that total order is actually not something we require for this problem. We really only need a happens before or causal ordering between these messages. We need to know, was A alive before it was dead, or was it dead before it was alive? We don't really need to care how A's liveness relates to B's liveness. And so the solution to this is basically a logical timestamp for state updates. The authors call this an incarnation number, but it operates really no differently than a logical timestamp. So now what we do is we append to every state update message, basically, so before we were sending alive and peer A, now we send alive peer A at time 0. This time value is globally maintained per peer. So the incarnation number for A is maintained independently from the incarnation number for B, C, and D. This is peer specific. But the key here, and how we avoid all sorts of nasty problems, is that it's only incremented by the peer. So only actually A can say, okay, I'm joining at time A, I'm alive. At some time later, someone comes around and says, at time 0, I suspect that A has failed. A then turns around and says, at time 1, I am alive. So basically, you refute the suspect message or the dead message by sending out a counter offer, so to speak, at a higher time. So now this kind of resolves the problem we had before, which is we receive the exact same messages, but this time they're annotated by version. So now if we apply kind of the state flow arc going through this, we have to respect the certain rule, which is the highest incarnation number wins, unless that message is a dead message. There's a little bit of subtlety around why that's the case, but basically, if you have a case in which one node, so suppose we basically suspect a node as having failed, that node refutes it. Some nodes in the cluster may have received this refutation while other nodes have not, and those nodes will mark that node as dead, and basically, by giving precedence to the dead message, there's an opportunity to refute it. It's kind of nuanced, but anyways, we mostly just respect the fact that the highest incarnation number wins. So in this case, we look at message Q1, the node was alive, node was suspect, node is marked dead at time 1. When we receive that alive message at time 0, we can safely throw it away because the version of our state is 1, and we know this message must have been reordered or it's a delivery from the past. It's no longer a relevant update. Message Q2, alive, suspect, alive, dead. Again, we both end up in the case where we believe the node is dead. So now we've solved the problem of basically, given a network that's able to run free to reorder message delivery, we can still arrive in a consistent state. So what we've done here is or what the authors, I should say, have done, is they've added the suspicion state. And what that has let us do is trade the failure detection latency by some configurable timeout, but we're now able to decrease our number of false positives and thus increase our accuracy. And this lets us plan for slow processes, degraded networks. But we still have that open question of completeness. And the way to see that is basically, this definition of strongly complete is that every faulty process must be detected by every non-faulty process eventually. And so the current technique is we just randomly pick a node to ping so that we are expecting to ping every node eventually. Unfortunately, this sentence has a lot of kind of very weak guarantees involved. Well, what does it mean for us to expect to ping a node eventually? Like, in the next hour, in the next year, we would like to know what that eventually means. We'd like some bound to it. Additionally, there's another problem, which is random doesn't necessarily mean there's no pathological conditions, right? As both Dilbert and XKCD have pointed out, this is a perfectly valid random number generator. So we'd like to get around this issue, and we'd like to be time-bounded. So the approach the paper takes is actually you take your set of peers, and you randomly sort them. So we have a random sorting of the peers, and then we just ping them in round robin. The cost of doing the sort is basically amortized constant, because you do the sort once, and then you use that sorted list for the next n operations. So it's effectively adds no additional overhead to what we're already doing, but now we've bounded our worst case situation. It's possible that every single node has sorted this list such that a given node is the final one in that list, and in the worst case, it's going to take interval times the number of nodes for someone to get around to pinging that node. So if we have 1,000 nodes, 1 second interval, we can say, hey, we guarantee that within 15 minutes we're going to detect it. It's a terrible, it's not a great situation, but luckily it's very pathological and it's really never going to happen in practice. But our expected cases, we're still going to be only one interval away from that original failure detection. But now we've removed that expected eventually case. So as an evaluation of kind of SWIM++, where do we stand? We basically now have moved from the eventual expected completeness to a time-bounded completeness. Great. Our speed of detection and accuracy now have this trade-off, which is we basically have a tune around the number of suspicion rounds that will allow. And again, this leads us to this vague high accuracy. So we saw that by selecting a reasonable number of indirect peers, like 3, we can effectively guard against packet loss. And given the kind of the application context, you can achieve fairly high accuracy by selecting the appropriate number of suspicion rounds. So if you happen to be NASA and you're running a real-time operating system and you can guarantee your job is going to schedule in 40 milliseconds, you don't need to worry about the case where the process is not going to respond for 90 seconds. If you're running, a 200 gig JVM, maybe you set that to an enormous number. And then the key here is that our network load is O of n. So it's actually reasonable for us to run this at 1,000 node, 10,000 node scale. Maybe you're Google, and maybe you can pull off 1 million. So the performance is then evaluated by the authors. They do it at a 56 node scale. We've implemented this in Surf, and we have real-world customers using it at 2,000 plus node scale. So we've been able to kind of evaluate it at a much bigger scale. And basically, our findings hold perfectly with what the authors promised us, which is the network load is effectively constant given the number of nodes in the cluster. So you're sending one ping message every second, whether you have 1 node or whether you have 2,000 nodes. So the network load is constant per node. The false positive rate they show is very low. In practice, we also see an incredibly low false positive rate. The constant time to failure detection, they show it's effectively, suspicion rounds multiplied by your thing. And in practice, we almost always see 7 seconds as well. And then there's a logarithmic increase in latency of information updates. This is just kind of the nature of gossip protocols themselves. You kind of have the diameter of your network increases logarithmically due to the nature of the gossip, which is great because even with 2,000 nodes, our update only takes 1 second. So it's more than acceptable. That's not to say SWIM doesn't have a number of limitations. The authors gloss over some of them, and we'll kind of cover them all and how they're addressed in SWIM. So I'm not going to spend too much time on this because we're going to go over each one of them in a little more detail, but this is just a little brief summary. So the first major problem with SWIM's approach to state updates is basically the latency is very high. And the reason for this is they only make use of piggybacking in SWIM. So that means if we pick a 1 second failure detection interval, we're only able to send 1 gossip message to 1 peer every second. This tends to cause a very slow rate, right? Because the problem now is your throughput is fixed. If you can only send 5 updates per packet, well, you're only sending 5 updates per second. If an entire rack of 40 machines joins or an entire rack fails, you might have to broadcast, hundreds of state update messages, and it's going to take you a few minutes to chew through that. So the approach we take in Surf is basically to decouple the state update gossip from the failure detection. So we run our failure detection on a 1 second interval, and we have a separate gossip timer that runs on a 200 millisecond interval. And where the failure detector, you send the ping, most of the time you're going to get the ACK back, which means you only have a chance to gossip with one peer. Our gossip timer, we always make use of a fan out of k. So regardless of the fact that the node responds to us successfully and acts, if there's a state update, we're still going to gossip it to 3 different peers. And because of this, because we're gossiping 5 times more often and sending it to 3 times more people, our effective throughput is much higher than otherwise if you're only using the piggybacking approach. And because of this, in the swim paper, their updates on 56 nodes, still take them 15 seconds. Our updates in a 2,000 node cluster happen in sub-second. The next issue that Swim doesn't really address particularly well is network partitions. So suppose we have a 4-node cluster, A, B, C, D, and we have a network partition such that A and B can talk to each other and C and D can talk to each other. Well, Swim will do the thing we expect, which is on both sides of the network, A and B will think they are alive and they'll think C and D are dead, and C and D will think they're alive and A and B are dead. And given the constraints of our network and the fact that no communication between these 2 clusters can happen, this is the best we would expect any membership protocol to be able to do. Unfortunately, we'd also want our membership protocol to be able to recover from this situation because it's something that might happen actually in practice. For example, A and B are sitting on one rack, C and D are on a different rack, and we happen to lose a switch that's connecting the 2 of them. This is something that actually happens surprisingly often, even in environments like public clouds. So the Swim approach to this is instead of purging the node immediately from that list of peers when we receive a dead message, what we do is we actually hold on to the dead nodes. So we're like, okay, we're going to transition this node to the dead state. We're going to stop reporting it as being alive to our client, but we're going to set them aside in this little buffer over here, and every once in a while, we're going to try and reconnect to them. And in practice, what this means is when the partition heals, which might take 10 seconds, it might take 2 hours, eventually we're able to reach that node again, and we'll be able to connect to them, and we're like, oh, great. Node A was able to talk to node C, and A and B and C and D are able to re-merge together into a single cluster and recover gracefully from this network partition. But now we have this different problem, which is we've taken this node that was marked as dead, and we're going to try and connect to it. But how long are we going to continue to try and reconnect? Because if C and D are actually legitimately dead, they're never coming back, right? And we don't want to sit around and hold on to dead nodes forever and keep connecting to them until the end of time. So to be able to kind of sanely stop retrying, what we'd really like to be able to do is distinguish between leaving the cluster intentionally and outright failing. And the distinction is important because when you leave a cluster, it's voluntary and there's no recovery necessary, right? The node has said, I want to leave. You're going to detect in the next 10 seconds that I'm not responding to pings, but don't worry about it. This is what I intended to do. Failing just means they're not responding to pings. Maybe there's a network partition. Maybe the process has crashed. Maybe my network card doesn't work anymore. Nobody knows what the real problem is here, but it's possible there's a partition, and we'd like to be able to automatically heal from this condition. And so the approach Surf takes is basically to add a notion of intents. So an intent is basically we just broadcast our intent to leave before we leave. So we broadcast, I'm node A, I'm about to leave at time 5, whatever, using the same incarnation clock. And the other nodes, when they see this message, they store it in a fixed size buffer. So they might maintain the last 100 intents they receive. And then what happens is when the node actually fails, so the failure detector says node A has stopped responding, mark it as dead, Surf looks aside and says, is there any intent to leave? If there was a corresponding intent to leave at the same incarnation time, we actually mark the node as left as opposed to failed, and this makes it so we don't have to retry, basically connecting to that node indefinitely. So that solves the problem of network partitions. A separate problem is actually joining or rejoining the cluster. So in the earlier slide we saw when node B wanted to join, it just sent a ping and it said node B is alive, right? And maybe it got back a message that said node C is alive. Well, that's great if there's only 3 nodes, but if there's 1,000 nodes, you're not going to be able to send back a state update saying, here are the other 1,000 nodes in the cluster. So how long is it going to take for a new node joining to be able to discover every node? Well, if all we do is rely on receiving a ping message from every node, then we expect it's going to take O of n time. We're going to have to wait until every single node in the cluster pings us to be like, oh, okay, you're alive. Oh, okay, you're alive too. And so this is incredibly slow if you're, at a large size cluster. So what we'd like to be able to do is somehow do better. We'd like to bootstrap around this problem. And so what we do in Surf, this is a fairly large modification, is that we actually add a TCP-based push-pull mechanism on top of the gossip. So when a node first joins, it picks, you have to know some initial joining member. So you reach out to that node over TCP, and you push your state to it. So this is the push part of this. You push and you say, hey, the list of nodes I know about is myself. What is the list of nodes you know about? And so then A will respond and push its state view of the world down. So it'll push down and say, hey, I know about nodes A, B, C, and D. Node D might be in the dead state. Node C might be in the suspect state. But A is basically able to do a full state dump and transfer all of that to B, so that B now doesn't have to wait 1,000 seconds. B instantly is basically up to date and a full-fledged member of this cluster. Additionally, I kind of skirted around this and said when we recover from partitions, we just rejoin the old node. Well, what does that even mean? It means that we actually attempt to do this anti-entropy mechanism on some interval. And so the reason we do that is, let's say you have that split and you have nodes A, B on one side and nodes C and D on the other side. Well, it's entirely feasible that you booted another 100 machines. You just went to AWS's console and you started going crazy. And so now it's actually A, B and the next 100 machines, and the other cluster is only C and D. So when this partition heals, you'd like C and D to also be able to quickly recover any missing state information they have. So in that case, when the partition heals and the push-pull state happens, C and D will now discover the 100 new nodes without waiting an additional 100 seconds, basically. This may seem somewhat familiar if you've read the bimodal multicast paper. It's a much earlier work, and they basically use opportunistic broadcast and multicast to send the message, and they also use an anti-entropy mechanism to recover from packet loss. So it was inspired by that paper and kind of applied in a slightly different way, but the end goal is basically to increase the speed of convergence time and to make it so you can join the cluster without waiting 1,000 seconds, basically. So given that we have the system that is able to provide highly reliable broadcasts, and it's giving us a list of peers that are alive, it seems like an excellent building block for systems. You're like, okay, well, if I want to build a distributed system, these are kind of giving me two of the major components I need. What would be really nice is if I can leverage the existing framework here and send a custom user payload. So for example, I want to build a leader election system on top. Maybe I want to be able to broadcast a message that says, hey, the new leader is node foo. So you should start directing all of your traffic to node foo. So supporting an application-specific payload is actually much more challenging than it might seem. And the reason for this is because effectively you now have unbounded state. So previously, the only state we had to remember is the list of nodes and whether they're in the alive, suspect, or dead state. So we have 1,000 nodes. They have 3 possible states. Great. There's a limit to the total state knowledge. And so we can do things like push and pull our state because, I'll just send you my whole list of 1,000 nodes. I can encode it in 2 bits what state that node is in. Great, it's not very large. Now the problem is users are able to send any amount of events with no sane way to basically compress that history. For example, maybe for some bizarre reason I like to keep track of time by just taking the time from NTP and broadcasting that as an event. There's no, well, actually that was a terrible example because you can compress that easily. But there's cases where you can't compress it. Exactly, there you go. You might have an unbounded number of bucket properties. So this is a kind of a crappy problem. Another crappy problem is deduplication of these payloads. So in the state update case, if I get 2 messages that say node A is alive at time 0, well, probably I just got a duplicate UDP message. Doesn't matter, I throw one away, it's irrelevant. Well, now what happens if I get 2 messages that both say, you should restart Apache? Well, did I get that same restart Apache message once, or did I actually get 2 different messages telling me to restart Apache? So we have an issue of deduplicating and dealing with the fact that networks are fun. And again, because networks are fun, we have an ordering issue, which is we receive start Apache and then stop Apache. Well, it kind of matters what order those are arriving in, right? So we'd like some ordering of events as well. So we get around kind of both of these issues by making use of Lamport clocks. And a Lamport clock is, again, it's a logical timestamp, kind of like an incarnation number, but they're now global. So where the incarnation number was specific to node A, A has an incarnation number that only A increments, the Lamport time is basically globally visible. So anytime you fire a user payload, that message is gossiped out to the entire network, which means the entire network sees the current Lamport time and is able to increment to the next time. And what this does is now we get a happens before ordering among all of our message, and additionally we get a deduplication. So if we get restart Apache time 5, restart Apache time 5, we can say, well, it's possible that these messages were different because independently they could have been generated. Lamport time only gives us a causal happens before ordering, so these two could have happened simultaneously. But for the purposes of our domain, we can just throw it away and treat it as a duplicate and say, well, if you really needed to send two messages duplicated within a 200 millisecond period, tough luck. But we get an ordering and we get deduplication that solves 95% of the application problems. And on top of this, basically, so now we have the unbounded state problem, and we'd like to kind of resolve that. So what we do is we keep a list of our recent events. So this is maybe the last 1,000 events we've seen, and we actually include that as part of our anti-entropy run. So when we have that cluster split, and it's A, B in the 100 nodes, and then C and D sitting on the other side, maybe we send an event that says, hey, deploy a new version of your application. Great, 100 nodes of our cluster see this message, 2 nodes of our cluster don't see the application deploy. Eventually the partition heals, anti-entropy takes place, they basically are able to replay the last 1,000 events and say, oh, this Lamport time, this event took place in the future, it's a message I never saw, and they're able to recover from this. And additionally, because we have this, Lamport gives us this causal ordering, events can actually be firing on both sides of the network partition, and when it clears, both sides will actually be able to recover and replay all the events. We'd also like pure metadata. So an example I gave before was we're building a leader election system, and maybe in that system, not all peers are considered equals. We might have some peers that are leaders, some that are clients, some that are standbys, whatever it may be. What we'd like to be able to do is, given a list of peers, I'd also like to attach arbitrary metadata to it. It'd be like, peer A is a server, peer B is a client, peer C is, whatever, a network switch. And the surf approach to this is we actually just inject this into the alive state update. And what's convenient about doing this is the state of any given node is already versioned using the incarnation number. So at time 0, when a node joins, it says, hey, I'm a client, and I just attach that metadata. But even if I'm still in the alive state and I want to transition from being a client to a server, I just send a new message out that says, I'm alive, I'm now a server, but this is at incarnation time 1. So I simply increment my version, change my metadata, gossip that out to the cluster, and the cluster is, we now get basically to attach arbitrary metadata to all of our nodes without really changing a whole lot. Another issue that isn't mentioned at all, but turns out to be an issue in production, is encryption. So SWIM doesn't talk at all. You have a peer-to-peer gossip. How do you encrypt and provide some form of confidentiality, integrity, authentication? We can't reasonably use SSL or TLS in this situation because it's stateless. We're sending UDP packets. There's no chance for us to send a connection. You send me something, I send you something. We're going to go talk to a CA authority. We're sending one packet. The RSA key is larger than the packet. It's not possible. So we basically make use of an AES GCM system. If you're like me, I don't know a whole lot about encryption, so I asked smarter people about it. They told me this is what I should use. And basically, it adds a little bit of overhead to our messages, but we get both verification and confidentiality. So every node in the cluster shares a symmetric key. All the messages can be encrypted, and the integrity is verified using basically a checksum. And Surf provides a key rotation mechanism on top of this. So on top of that, we have a way to say everyone is at key 1, install a new key 2, and so all nodes have some concept of a key ring, so you can have an arbitrary number of keys installed. So you install a new version of your key, you ask everyone, do you have version 2 of your key? Great, rotate and move to using key 2, delete key 1. So basically you do this in a multi-step fashion, but you can actually rotate keys in a safe way, which is important if you're selling to enterprise. Okay, so implementations. So we wanted to keep very true to the SWIM paper, part of it just for being able to share it in a more in a pure context. So what we did is we actually implemented SWIM in its own library called MemberList. You can find it on GitHub. It includes some modifications that are necessary for Surf which sits above it. So some of these things like the TCP level stuff, the encryption, the non-piggyback gossip, these are all things that are not part of SWIM, but they can actually all be disabled using configuration flags in memberlist. So with memberlist, you can basically set your flag such that you get a pure, true SWIM implementation. The surf library wraps that one and provides all the niceties we just discussed. So, memberlist, the SWIM protocol doesn't give you key rotation and all these nice things. So surf builds on top of that and provides a lot of user-facing APIs and that kind of stuff. Confusingly enough, we then build a project called Surf, which is a CLI command tool, which uses the Surf library, and also Consul. And I'll talk about these two in a little more detail. So the Surf project, like I said, is a little confusing. It provides cluster membership, failure detection, and orchestration. Well, it's kind of easy to provide the first two because we're just using Surf here. So Surf is already giving us the membership and failure detection. The CLI wraps that. And it provides basically an executable agent that you can run. It's a CLI. It's a lot easier to use than a library. You have an RPC interface. It provides custom events and a request response system. So for example, you can send a request to every node and be like, run the uptime command, return the results to me. That message gets gossiped out almost instantly to clusters of any side, and then they send the response directly back, and you're like, cool, here's the uptime of all my nodes. So this is the Surf project, and it just makes use of the Surf library. People don't realize you can just embed the Surf library in your own project and do whatever you want with it. The CLI is totally decoupled. The Consul project is a much larger scope project. So it provides service discovery, configuration, and orchestration, and it actually also makes use of Surf as a critical underlying building block. So it supports multi-data center. So you can deploy Consul into different data centers, and I could be in the foo data center and say, hey, give me the list of live nodes in bar. And the way we enable this is each of our data centers is actually gossiping across the WAN, making use of Surf. So they become aware of new data centers by using a membership protocol. If we happen to lose a WAN link, the entire foo data center might fall off of the internet, and our other data centers can gracefully detect this and continue routing traffic between each other, and only foo is affected by this. In addition to using Surf across the WAN, we also use Surf within a given data center to do node discovery. So given that you have 1,000 nodes running in AWS, you boot that 1,001 node, it simply joins any node that it knows about, maybe over, there's a well-known IP or it uses DNS, but it joins one node, and through the gossip level, it's able to discover every node in the cluster and find the appropriate servers that it can route requests through and do service discovery. It also acts as an event bus, so events like leader election or user events can be embedded. So for example, you can use Consul to orchestrate deploys of your application. You can do things like, Consul deploy, Rails, put in a Git SHA, and then your servers know what to do with that. They go and pull down the right commit and do their thing. And the last piece, which I think is kind of the coolest and I geek out over, is because we have a distributed failure detector, it actually enables Consul to provide distributed locking. So in both Zookeeper as well as Google Chubby, the way distributed locking is done is, all your nodes, they go through a consistent serializable system, and they say, hey, acquire key foo. Well, the problem is if you acquire a key foo and then you happen to die, then you're holding that lock until the end of time, and no one else can make any progress. So this is incredibly crappy. And so what you'd like to be able to do is say, like, okay, I'd like to acquire key foo, but if I die, release the thing automatically so someone else can pick up the key and continue doing work. Well, it turns out that the state of the art in doing that is actually using heart beating. So the way both Zookeeper and Google Chubby work is you connect to Zookeeper and Chubby, and you say, I'm starting a session, and the server says, great, every 10 seconds, send me a ping that says you're still alive. And so you connect to Zookeeper, you start sending ping messages that I'm alive, and then you say, acquire key foo. If at some point you stop sending those messages, or in the worst case, Zookeeper decides to GC itself and you're still sending those messages, those heartbeats don't get through, it's marked as a failure and your key gets released. However, because Consul makes use of a distributed failure detector, we're able to do distributed locking in what I think is a much more elegant way, which is you acquire key foo, and it's associated with the node that owns it. So if Consul, through its gossip layer, ever detects that that node has failed, it can automatically release the key, but it's not burdened with handling, heartbeat messages from thousands of nodes. Instead, that work of checking for failures is distributed among the entire cluster. So the load on Zookeeper and Chubby is actually linear with the number of nodes in your cluster, while with Consul, it's actually constant. Doesn't matter how many nodes you have, there's no additional work on the servers. This happens to make its distributed locking much more scalable and much less prone to a GC pause taking it down. So in conclusion, SWIM is a fantastic membership protocol. Given the rubric that the paper uses to evaluate it, obviously there's some selection bias there, but you could pick other rubrics, and it really is a great protocol. It solves a lot of really hard problems. It does have a handful of limitations. None of them are disastrous, and we've addressed all of them in Surf, which is open source. Feel free to make use of it. And kind of as a closing, we found that distributed systems love gossip-based membership. They just kind of fit so well together. It's the glove that just fits, right? It's robust, it's peer-to-peer, there's no centralization, they handle packet loss. It's a dream. It's a dream come true for distributed systems. So with that, I'd like to finish the talk. So if there's any questions, I'm more than happy to answer them.
How does the distributed locking deal with network partitions?
So the network partition actually looks like a failure. So what'll happen is your node foo, you acquire lock bar, you're partitioned from the server, so from the server's perspective, it looks like you have failed, it releases that lock. So there's exactly. So there is a natural trade-off between safety and liveness is basically the fundamental trade-off here, which is safety is the property that no two nodes will ever basically hold the same lock at the same time. That turns out to be an incredibly simple thing to provide. If node foo acquires the lock, well, I don't ever release it unless node foo explicitly tells me to. In this way, it's not possible for any two nodes to ever have it. Unfortunately, you've sacrificed a different property, which is liveness, which is suppose node foo acquires the lock and then dies. Well, now no progress can ever be made in the system. You effectively are live locked, right? So no one else can do any work. The node that was supposed to hold the lock and whatever process the event queue, whatever it was going to do, is not doing that, and now your system will never ever make progress. So you basically have this fundamental trade-off you have to make between liveness and safety. And so Consul actually gives you both options. So when you acquire a lock, you can associate it with a number of health checks. That Surf health check is actually just a default, so you can disable that. So if you want, you can acquire a lock and say, in this particular case, my application cannot tolerate a lack of safety, for whatever reason. You're doing something that can't deal with this. So you can say, don't ever release this lock until I explicitly tell you to, and Consul will happily oblige. In the other case, most of the time, it's like you only want one person sending the emails from the event queue at a time. You'd rather have liveness as opposed to safety, so you're willing to make this trade-off, basically. And then the other way you guard against this, basically, is this is actually comes from Google Chubby, is what you do is you have kind of a grace period in which you won't let someone else acquire the lock if it was released due to a failure. So what I mean by this is node foo acquires the lock. Node foo is partitioned from the network. Consul detects this, let's say, in 7 seconds. It releases the lock immediately, but it won't allow anyone else to acquire that lock for the next minute. And what this guards against is basically that node foo should be able to detect within the next minute that it can't talk to Consul, because it's going to be like, it should, as part of the leader election, you should be trying to establish a connection to Consul. Its TCP connection is going to break because it's partitioned. It's going to be like, oh crap, I can't talk to Consul. I'm going to stop processing whatever it was I'm doing. So the node that previously had the lock detects that it's partitioned. It stops operating. On the other side of the cluster, Consul refuses to give away the lock for the next minute, giving that node time to basically back off whatever it's doing. And then eventually, at the end of the minute, someone else can acquire the lock, and your system has liveness. So the minute is kind of it's a total heuristic hack. It's entirely possible your client is not written well, and you have two clients on both sides that think they own the lock. But this is kind of a fundamental impossibility. So we do what we can. Mm-hmm. Sure. Sure, yeah, but in this case, you're basically, Yeah, exactly. But this is exactly kind of the same kind of operation as doing the keeping a connection alive to console. What that means is effectively, in that case, what you're saying is on every operation before I do it, I'm going to verify that I have a thing. Yeah. Sure. Okay. Yeah. I mean, it kind of depends on it's a bit of hair splitting, right? Because in that case, what's going to happen is you have the network partition. That node foo is going to try to contact console because on every operation you've told it it should be doing it, right? So it cannot connect to console, right? Because it's partitioned. So it won't process it, right? But because you've told your lock, I want safety, even in the face of a thing, don't give it away. Well, this node who previously held the lock can't connect to console and can't complete the operation. And on the other side, console, you told it, don't release my lock. It cannot give it to anyone else. So now on both sides of the thing, no one is able to make any progress. That's what we do. Exactly, and that's the current approach. It does sacrifice safety because, like you said, it depends on the client behaving properly. If the client does not run every operation through console ahead of time and check effectively. Correct. I agree totally. Console does exactly as you suggest. So I do agree. In a well-written application case, you can effectively have both. In the case, the problem is basically console can't be written in such a way that it can guard against faulty clients violating safety. It's impossible as the authors of console for us to ever provide an API that a client can't violate, basically, is what I'm saying. Sure, yeah, it is. Yeah, I agree. I agree. Yeah, I mean, we often get this question. We don't attempt to provide Byzantine fault tolerance. We don't attempt to guard against client errors. You know, we'll do our best. There's some validation we can do to be like, that's not a valid session, or your health check is already failing. There's some things we can do, but we can't do everything, unfortunately. But like I said, in practice, what you find, as you said, is it's really not an issue. There's enough safeguards there that realistically you're getting safety and liveness. But, you know, there's that. We try to be very careful about what we promise, and it's impossible for us to promise both. Yeah. Yeah. Yeah, exactly. Yeah. Sure. Well, I'm just going to suggest you to take this offline in case there's other questions. Sure. Yeah. Yeah. Exactly. Exactly. Yeah. Yeah. That's a good question. Yeah. So we looked at using vector clocks, and the problem with a vector clock is you have to actually, you keep basically, I apologize for those of you who aren't familiar necessarily with them, but you keep an independent timestamp for every client in the system. The problem we had with this, and then basically you can get stronger notions of ordering. The problem that we had was we had to keep track of every client in the system, and because this is gossip, we're trying to fit it into a single UDP packet. So if we have 1,000 clients in our system and we have to represent 1,000 timestamps, you know, and they're 8 bytes wide because they're 64 bits, so on and so forth. All of a sudden, you know, our 1,500 byte packet now doesn't look very spacious because you know 5 or 6 different packets have to represent a single vector clock. Right. I saw the talk. It was fantastic. I was at Recon. Yep. Right, right. Right, and that's the appropriate use of a membership protocol. By design, Swim wasn't meant to be, a high throughput system. It was just like, well, we have all of this machinery in place, all of it's written, I have a few hundred spare bytes. What if I just throw in an application payload in there, right? So it's certainly not designed to, build your video multicasting system on top of it. That's probably a poor use of Swim, right? It'll implode under the load. But if you just need to send a little uptime message once in a while, it works pretty well. Yeah. So again, what we use it for in console is mostly for the membership as well as for the failure detection stuff. The event stuff is just used to be like, hey, there's been a new leader elected, or a new data center is available, or a new node has joined our cluster. Some things that are relevant at the application level, and then we make use of that information to do more appropriate overlay routing on top of that. Yeah. Yeah, so I think, it's a great question. And I think the key driver of why you need the fully connected mesh. Oh, sorry. So the question was, does Swim require a fully connected network? And so what that means is basically, does every node that we consider our peer have to be able to talk to every other node? So for every given node, should every node be able to reach every other node? So you can think of this as a WAN network. So we can't, for example, have 500 of our nodes on one LAN, and then 500 nodes on a different LAN with only one link interconnecting them, like a VPN or something. Because in that case, it's not fully connected. There's intermediate. We have to do multi-hop routing. And so really what that comes down to and why we can't do that is because of the randomized failure detector. So the properties of the randomized failure detector rely on the fact that it's fully connected. So if we don't have a fully connected grid, then we don't get that constant load. Because all of a sudden you have that 500 node, and there's only two peers that connect the two. Their load is no longer constant with respect to the size of the cluster. Their load is now linear with respect to the size of the cluster. And so if you add that little caveat, which is to say, okay, we require a fully connected cluster, then we can alleviate this problem. So one way around this, so Consul has this problem. Consul makes use of Surf both to discover nodes within a data center as well as to discover multiple data centers. Well, immediately this is a non-fully connected problem, right? Because one data center, it's sitting in AWS, great, every node talks to every other node. The other data center is sitting in GCE, every node talks to every other node, but they can't talk to each other because they're both private networks that are not routable to each other. But Consul still has a way of routing traffic between each other using gossip. And the way it gets around this is by layering multiple different gossip rings together. So you have one ring, which is your WAN ring, which expects that all of them are talking over a public IP address. They're all reachable. And then you have a separate ring, which is local to the data center, private IP address, and you actually handle the overlay routing at a higher level. So we basically can route the traffic to these border nodes. The border nodes are able to discover their peers through the other ring, and they basically do multi-hop routing at the application level. But yeah, that's a limitation.
So this is less a Swim question, more a Surf question. Did you guys look at using something like SCGP, which has hybrid reliability and non-reliable unordered message syntax, or semantics rather?
Quite honestly, we did not. We did not look at it, no. I don't even know why we didn't look at it, but I just know we didn't look at it. That's probably why we didn't use it, honestly. And I think I probably looked at the spec and was like, no, don't think so. If you port it to C for me, I will gladly use it. Well, you'll never meet the author because they'll kill themselves. Any other questions? Awesome, cool. Thanks a lot, guys.